Okay, today we're talking about ionization energy. And ionization energy is that energy that's required to completely remove an electron from an atom. The ionization energy depends upon the attraction between the positively charged nucleus and the negatively charged electron that's being removed. It also is affected by the repulsion between the negatively charged electrons themselves. We can see how all this comes together with Coulomb's law. Coulomb's law tells me about the force of attraction and how it is affected by the charge on the nucleus and the charge on the electron. Oppositely charged objects will attract one another. So we have the force of attraction here. But the distance between the objects also affects the force of attraction. The greater the distance, the less the force. So the outermost electron is going to feel the weakest force of attraction. Now we also call this the effective nuclear charge. The effective nuclear charge is what the outermost electron actually feels. You see, the outermost electron is both attracted to the nucleus and it's repelled by all the other electrons that are closer to the nucleus. So therefore those extra electrons provide what's called a shielding effect and reduce the charge, or what appears to be the charge, on the nucleus. And so we call that the effective nuclear charge. Now, you were given a table with some ionization energies, and it's reproduced here. Notice that the ionization energy is high for hydrogen and helium. Notice that it's pretty low for lithium, and that it gradually increases. We're going to plot those on a graph. Here we see a graph of the ionization energy versus atomic number. So on the x-axis down here we have the atomic number, and over here we have the ionization energy. Notice that we start off in the middle with hydrogen. Ionization energy increases dramatically for helium, and then it drops even more dramatically for lithium. Then it works its way back up until we get to neon again. A big drop to sodium, works our way back up to argon, big drop to potassium. Slowly we go across the transition metals, back up to krypton, another inert gas, down to rubidium, and then we have xenon and cesium, and there we stopped. And what do you notice about all those? Well, clearly you ought to see that helium and neon, argon, krypton, and xenon are all inert gases. And lithium, sodium, potassium, rubidium, and cesium are all alkali metals. Now, why does helium have a very large ionization energy? That means there's a very strong attraction between the nucleus and the electron. Since that electron is at a fairly low energy, then it needs a great deal of energy to remove it. On the other hand, the ionization energy of lithium is quite low. That means that the electron that's being removed from a lithium atom is already at a higher energy, and therefore little additional energy is needed to remove it. We see that ionization energy is periodic. As we mentioned earlier, you'll notice that all of the peaks are the inert gases, and all the valleys are the alkali metals. And you notice that we get this same repetitive pattern for each period. So in the second period, the ionization energy increases as we go from left to right, from lithium to neon. That pattern is reproduced in the third period as we go from sodium to argon, in the fourth period from potassium to krypton, and in the fifth period from rubidium to xenon. And chances are, if we get down to cesium, it would be repeated in that period as well. You notice that in these two, we only have 8 electrons in the period. In this one and in this one, we've added in the transition metals, so that makes for a bigger gap in between. Here we see just the first 3 periods on the periodic table. First period, of course, just goes from hydrogen to helium. But you'll notice that in the second period we have a general increase in ionization energy. What do you think would account for that increase in ionization energy? When we get to the transition metals, we notice that there's less of an increase. All along the transition metals, these ionization energies are fairly close. That must mean that the effective nuclear charge is relatively the same all the way across the transition metals. This also accounts for why the size of the transition metals are all very close together.